Okay, so what I'm going to talk about is the distributed ray tracing paper by Cook, Porter, and Carpenter. It came out in the ACM SIGGRAPH proceedings in 1984, and I expect you to download a copy of that and read it. It was listed in the syllabus as the reading for today. And it's in the ACM Digital Library. Those weren't journal publications at that point. It's way before SIGGRAPH joined the ACM Transactions on Graphics, but you can get it under the ACM Digital Library page through the electronic databases at the library, and look up conferences, and there's lots of SIGGRAPH conferences. You have to get the main one that's down near the bottom of the page there. So what they did is they used the concept of Monte Carlo sampling that we're talking about in the last couple times to get a lot of special effects that hadn't been done before, or at least hadn't been done very efficiently. So one was shadow penumbras. That means the partial occlusion of the light source that gives you soft shadows for direct lighting. Another was glossy reflections. That means if you don't have a perfect mirror, but you have something that's only slightly bumpy, the same effect that gives you an imperfect, you don't get a point highlight from a light source that's a point source. You get a sort of a Phong blur of the light source. You get a blur of then everything else that's reflected. Another thing that gives you blur is depth of field, which I'll spend a lot of time today talking about. That's the idea that a camera lens is only perfectly focused on a single plane of focus, and things in front of the plane or behind the plane are slightly out of focus. And that's a sort of an artistic effect, and it's also an effect you need if you want to intercut computer animation with live footage, or make a computer animated character interact with live characters. Another thing you have to do if you want to match live photography with computer animation is motion blur, because any real camera has the shutter open for a finite amount of time, and if they're moving objects, their motion will cause a blur in the image, and this Monte Carlo sampling should get that also. Anti-aliasing. So before this paper came out, people were already using multiple samples per pixel for ray tracing, just to make sure that, like on your homework, you see jagged edges of your sphere. And if you had multiple samples per pixel, you could sort of smooth out those edges by getting mixtures of the color of the sphere and the color behind it, depending on where the subpixel ray sample intersected. So basically what these authors showed is if you're already doing this, you can get all these other effects for very little extra cost, because you're already using multiple rays per pixel. So let me start with the depth of field effect. The idea is if you have a thin lens here like this, and you have rays coming in from infinity, the effect of the lens is to refract these rays so that they all end up at the same point on, say, the film. And that means rays which are coming in from a different direction, but still parallel rays, will focus at a different point on the lens. But the point will depend only on the direction the rays are coming from. Okay, so this length here is called the focal length of the lens. And suppose now we have an object that isn't at infinity. So now we have some object here. Let me draw this same lens here. And rays are coming in, but they're not parallel. Well, if the parallel rays focused here, rays which are not parallel are going to focus let me think about it. I guess they'll focus somewhat farther away, right? Because these won't be able to be bent up completely as much, so they'll probably focus at some other point but behind the lens, right? The ray that goes right through the center of the lens will also hit that point. And so what you're going to get is a circle of confusion on the screen. And that means that what would have been, say, a point light source is going to end up filling up a whole circle. You can think about it like a cone of rays here and then converging on a cone here to this point and intersecting here in some sort of circle. So, but there is a distance, say, v, to, say, the film plane of the camera. If you move the lens farther away from the film plane, which is what you do when you focus the lens, you can make objects at this distance, which I'll call P, from the lens focus. And there's a formula relating this number, and this number, which is the focal length of the lens. And that formula says, maybe I'll write it on this board, F V plus F P equals P V. So when we study refraction, which I've sort of keep saying I'm putting off till the end of further on in the quarter after I describe all the stuff you're going to need for the homework, we may be able to derive this equation from the rules about refraction. But what you can do then is, if you know V, you can find P, and if you know P, you can find V. So let's assume we know V. That means we've got the film at a certain distance from the camera, and we want to find out how far from the camera this focal plane is. So this is the focal plane, or plane of focus, and this is the image plane here where the film is. So let's see, that means we want to solve this for P, so FP, why don't I say minus PV equals, see, how am I going to do this? I'm moving everything to the other side of the equation. I better do it the other way around because I want to be, no, that's probably okay. I've got the things multiplying P, and then here is minus FV here. So that means I can say P equals minus FV over F minus V. Now V is actually going to be farther than F, right? Because things that were at infinity, you never want to focus past infinity, then everything will be blurred. So it's probably better to write this as FV over V minus F. Then the numerator and denominator are both positive. Okay, so now suppose we start with a point on this focal plane, and we want to figure out what rays from the scene converge on this point. Basically, we've got to come out this cone to the lens, and then we've got to come to this point, say, so let me take this point Q on the focal plane, that this point, why don't I call it K in the image, corresponds to. So that means we have a cone of rays coming out from K to the lens, and then that cone comes back together again at the point Q, and then continues opening up again past Q. So if we want to find the contribution of everything in the scene here, either in this part past Q or in this part between Q and the front, basically what we have to do is we have to sample a point L on the lens and figure out where the ray from K to L refracts and where it goes into the scene. And then if we take enough random points, basically it's equivalent to integrating over the area of the lens and then getting all the rays that contribute to the irradiance at this point K, which is going to be, you have a CCD sensor or something, or film chemistry that's gathering that light energy. So what we have to do is we have to go since we know all these rays are refracted by the lens, so they go through the point Q, all we have to do is go from L to the point Q and consider this ray that goes in this direction out through the scene. So basically, given K on the image plane, we pick a random point L. Why don't I say L in terms of U and V, where U and V are parameters that describe, say, horizontal and vertical coordinates on the plane of the lens. On the lens. And basically, now what we do before that is we trace, because this is good for all of the rays. I should have said it first. Trace a ray from K through the center of the lens. So here's the center C, and this ray here doesn't get refracted, right? Or, it may get refracted across a little bit, but then it continues off in the same direction because these planes are parallel, basically, at the center of the lens. If you think of a piece of a sphere and a piece of a sphere here and really close to the center, if the lens is thin, it's going to continue in the same direction. Okay, so basically that's a straight line. And where it intersects this focal plane at distance P, which we can compute knowing, what that distance V is from that formula, we can figure out the plane Q, the point Q. Until it intersects the focal plane at a point Q. Q depends on K, so I'll say Q depends on X, Y. X, Y are coordinates, so why don't I say with coordinates? These are coordinates in the image plane, basically pixel coordinates or subpixel precision locations on that image plane, X, Y, and this is coordinates on lens plane are U and V. And then we draw a ray from the point on the lens to Q. Okay, so that ray, so why don't I call it a ray R? The ray R has origin and a direction. And the origin of the ray is just this point L, which depends on the parameters in the lens plane. And the direction, we can say its direction capital theta. Eventually it's going to be the light coming into the lens from the environment. So I'm sort of using the book's notation for the incoming light direction. This depends on X, Y, U, and V, because what it is the direction Q, which dependent on X and Y, minus L, dependent on U and V, divided by the absolute value of Q minus L to make it a unit direction vector. Okay, so if we try and get the light coming to not a single pixel, but an area here. If the pixel name is ij, then depends on the convention. In OpenGL, say pixels are integers with a usually it's the lower left-hand corner, so it's going from I to I plus 1. And so basically, if you think about what they usually use in computer graphics, they think of the sensor as actually having the whole area of the pixel. Actually, on a CCD, there's some space between the sensors. If you really wanted to simulate it, it may be slightly different geometry. But let's assume for anti-aliasing, we're trying to integrate over the whole pixel. Then what we want to do is we want to think of computing an integral, which is the integral from x equals I to I plus 1. Let's see. Actually, x is a j. We talk about row and column. And the y is the I. Is that, when you do a pixel array, I don't remember how you do it. Who knows? I think the fastest changing index is the horizontal one. And in a matrix, is that I or j? That's column, right? So it's the other way around. So x goes to along. Is that right? Who knows what it is? Let's say, and this is dx, and say y equals I to I plus 1. I think dy. I can't even remember in C, which is the most rapidly changing index, the first or the last? Last. In that case, I've done it correctly. Because I think in the convention of how you store an array, it's the, when you feed it, like I draw pixels, the x changes most rapidly. But I think my notes are backwards, so maybe I won't be this consistent for the rest of the time. And we also want to integrate for uv in the lens circle, right, to get the effect of the depth of field for every point xy in the pixel. And I also talked about motion blur. How can you do motion blur? Basically, the shutter is open from time. So this is du dv, and this is, say, between shutter open time from t1 to t2. And the way you get motion blur is once you pick a sample time, you move all the objects. The objects are sort of got some animation program. This is how they move, but not just per frame. For any instant floating point value of time, even between frame numbers, during this shutter open interval, you can find the positions of all the objects. And then you trace the ray at that position. At that instant of time, and for that sample, you will be sampling where they are at that instant of time. And since different samples will get them, say this is moving across the screen, different samples will catch it at different times. Sometimes you'll see my shirt, and sometimes you'll see this piece of paper. This piece of paper will appear blurred. Even the writing on the paper will appear blurred. So what are we looking at then? We're looking at the light hitting the point uv on the lens. That's the origin of this ray from direction theta of u v x y. And that light depends on the environment, and the environment depends on the time, because we're moving the objects. And so this is a 5-dimensional integral. Now, if we were also considering the effect of an area light source, then maybe we're going to compute direct illumination at that point where that ray hits the scene. And then we have to integrate the direct illumination over the area of the light source. Right? Remember, I separated direct illumination from diffuse reflection illumination of the whole environment, and that got integrated over the lights, probably per area of the light source. So we're sampling the light source to compute the direct illumination at that point. That makes it 2 dimensions on the light source. Maybe that's 7 dimensions. You might also want to simulate glossy reflection, which means, or even diffuse reflection. The reflected ray can go out in the environment. Then it's not just over the light source, it's probably sampling angles, like I did last time when I was computing the diffuse illumination by sampling on the hemisphere. So you may have lots of dimensions to integrate. And so what made me most excited when I saw this paper is that you don't need to have any more rays than you already need to get good anti-aliasing. Because for each of those subpixel locations, you can pick a random number u and v and a random t. So let me talk about the worst case anti-aliasing, where you have a pixel, say with an edge going through it, and here is white, and here is black. And the probability, say, is p for white and 1 minus p for black, right? Because p is maybe this area, this is a 1 by 1 pixel in our convention. So the area is 1, and if the fraction p of the area is white and the rest is black, then we have a random variable which is 1 with probability p and 0 with probability okay, this is about the, if you think of the range of colors as going from 0 to 1 like it is in OpenGL with the floats, then this is the worst case you could get. Most contrast, that the samples will be either black or white. So what's the variance? This is called a Bernoulli distribution. And the variance, well, first of all, the mean. So x is this random variable. The expectation of x is, there are only two possibilities. So it's the sum, say, I equals 0 to 1 of xi pi. Well, let me just write it out, right? When we're talking with 0, we have q, this probability q is 1 minus p. So it's 1 minus p times, probably should put the value x in front. That's why I've written it here. Plus 1 times the probability of getting a 1. And this is 0 and this is 1, so it's just p. So the expected value is p, right? If the fraction of the area of p is white and the rest is black, that's the expected value of your, that's actually the integral of the radiance over this pixel. It's that equals the area that it's white. What's the variance? Well, that's the sum I equals 0 to 1 of xi minus the expected value of x times p squared times pi, right? This is the, before we had an integral, this was the discrete case that I talked about the period before that. And so let's see, if xi is 0, we have 0 minus the mean squared, and the probability of getting 0 is 1 minus p, plus, see, if xi is 1, then this thing is 1 minus p squared, and the probability of getting 1 is p. So this is actually p squared times 1 minus p plus 1 minus p squared times p. And I can factor p times 1 minus p out of this, right? And this thing has a p times that common factor, and this has a 1 minus p, an extra 1 minus p times that common factor. And p plus 1 minus p is just 1, so the answer is p times 1 minus p, or p squared minus p. So let me do a little calculus. I think I can remember it enough to write it over here. I want to find the, so for people who came late, you need to read this paper. If f of p is p squared minus p, that's p times 1 minus p. I just multiplied through. Then f prime of p is 2p minus 1, and that means that the critical value, it's a maximum in this case, is when this is 0, so 2p equals 1, p equals a half. Like, that's the maximum. If I go from 0 to 1 and I plot p squared minus p, it's this parabola here. And its maximum is right in the middle at p equals a half, and its value is a half. Let's see. It's p minus p squared. Did I multiply it through wrong? I did. I said p squared minus p. It's the same problem I made in my notes the first time. If we go way over here, p times 1, this is the plus term here, and the minus p squared. Because I thought I was getting a negative answer here. I drew the right graph, but this was p minus p squared, so the derivative, well, you can just think of the minus here and the plus here. I'm still solving the same equation. But now, at p equals a half, p squared minus p, p minus p squared is a half minus a quarter equals a half. So the worst is a quarter. The worst possible variance you can get is a quarter, and the variance gets less if more of it is white or more of it is black. Okay, so in general, and you can think about, whatever this integral is, it has a certain probability. In the worst case, it would have a certain probability of being in certain positions as black and certain positions as white. So the variance of any single estimate is no bigger than 1/4. So if we picked random x and y within the pixel, random u and v here, and random t there, no matter how we do it, and the variance of any sample is at most a quarter in this context of the maximum brightness of the scene being 1. So if we take IN, the answer with n samples, the variance of that, which I guess I've called sigma squared n before, is 1 over n times the variance. Well, sigma squared was a quarter. So that means sigma itself looks like 1/2 times 1 over the square root of n. And of course, in any pixel that's got less than maximum contrast in other places, everywhere, it's going to be less. So what this says is you can actually sample over 5 dimensions by sampling over the pixel first for the anti-aliasing. In fact, you could even use jittered sampling for that. And for each of those samples, pick random u and v and so forth. So say you had n by n pixels, n by n subpixels that you were jittering on. And I think I'll have time at the end of the period to show why that's superior. But so you have, say, 5 by 5. See if I can draw 5 by 5 subpixels here. And in each of those, you pick this random xi, yi. Well, you'd think to sample properly, this is over the pixel. You might think for the lens, well, we can't draw rectangles, but in polar coordinates, we can basically, what you would have to do is, pick equal area rings here. Right? So they're thinner near the edges. Then you could divide 5 sectors, if you wanted 5 by 5 here too, and 5 areas here, so that the spacing here was bigger than the spacing there, so that this area is actually equal to that area, and so forth. You can figure out how to do that. That's just one of these cumulative distribution function schemes. And so we'd have to pick u and v in this picture, and then t when in the interval. So say we divided the interval in 5 parts. Well, now it looks like we have 5 to the 5th samples. What is that? That's 25 times, so it's 3,125, I think, is 5 to the 5th. But you don't really need to do that. Because what you can do is you can choose a bunch of jittered samples in these squares. First of all, if you weren't doing jittering at all, you could certainly choose each of those x, y, and say r, theta to be random numbers with the proper distribution to get you equal probability on the lens and on here. And you would be able to just do this variant. You'd still get this variance scheme this way. But if you wanted to use jittering, and I'm going to try and show you at the end of the period why jittering is better, you could also choose capital N. This is m squared equals capital N, where m is 5 by 5 in my illustration. You could choose capital N of these samples, one in each of these little annular sectors on the sphere. And you could choose, I guess you really want 25 of these, right, to correspond. And you could choose a ti in this. And then what you do is you make a random permutation. So this isn't necessarily assigned to this lower left-hand corner here. It's assigned to some other random one. So for each pixel, say you make an independent random permutation that matches one of these to one of those to one of those. And they have to be random. The samples have to be uncorrelated. Because imagine we had this pixel here, and imagine, we counted these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 or something. And imagine we had a moving edge of a polygonal object moving across the pixels like that, right? And suppose it was here at time 0, and here at time 1/5, and here at time 2/5, here at time 3/5, and here at time 4/5. If we got this order to be the same as this order, right, in time, it's going to be visible at every sample. And you're not going to get the proper blur. So the permutation makes these subpixel positions uncorrelated with the subpixel intervals you use here, if it's a random permutation. And the book gives an example that they show n-rook sampling, where they just say, suppose you had to get one sample in one variable and one sample in another variable. And what you want then is, say, here are the 5 regions for this variable, and here are the 5 regions for that variable. Unfortunately, the book called them x and y, which makes you think of subpixel. But really, they just stand for like t and, some other thing that, or one of those guys. And you pick a random permutation, which means you're picking positions here. So in this first x, you're going to pick the first y. In the second x, you're going to pick the third y. In the third x, you're going to pick the second y. Maybe this is the last, and this is the next to last or something. So this is a case of a permutation, which specifies which y interval you pick for each x interval. And if you have one in each column and one in each row, you're sampling x well with jittered sampling for x and sampling y well for jittered sampling for y. And that's sort of the idea of a permutation for each of these things. Okay, so what about diffuse reflections? Well, we talked about that last time, right? For diffuse reflections, sample by weighting by the cosine theta. We want LR. This is what I had last time. I'm not going to write out all the variables. It was L times F times the cosine term d omega. And we sampled proportional to this cosine term, because we didn't know anything else about the scene or the BRDF. In fact, the thing I was going to apply that one to case 2 is perfectly diffuse reflection. The BRDF is a constant anyway. And what I said earlier in the period is for direct illumination, sample over area of light sources. Remember, I broke up the direct and the indirect and showed one over the area and one over. Okay, now these two I expect you to do for the following assignment. These, I just erased them. I wanted motion blur and depth of field, and anti-aliasing in the next assignment. And in the following assignment, I want diffuse reflections. I said global illumination, but really I just want diffuse. And I want sampling over the light sources to get the shadow penumbras. For glossy reflection, that's when this isn't constant. Then probably you want to sample according to the product of these two. Directions by the product of the FR times the cosine. And I was going to show you that today, but I'm not sure I'll have time because what I want to talk about is why jittering is good. So this isn't the full detail of why jittering is no worse than not jittering and sometimes helps. This is a case where for sure it helps. And this is jittering for anti-aliasing object edges. So what I'm going to assume is here's my pixel, and here is a polygon edge, and I'm going to do this worst case again. Here's white, and here's black. And what I'm going to use is the fact that this is monotone increasing or monotone decreasing, so that it'll intersect a horizontal line or a vertical line at most once. And that means I can handle a case that I was talking about before, and you're like in your homework, where you have an edge of a sphere here. I mean, it's not going to handle a sphere like this, or even a part which goes up and down in the same pixel, because then, you can intersect more than once. But suppose we have a monotone thing like this, and we divide up into subpixels. Maybe I'll try to do 8 of them. And I'll ask, how many pixels can this edge cross? So because it's monotone, it's going to cross these 7 lines at most, each of them at most once. And also these 7 lines, each of them at most once. So if I have m by m, it can cross, so a monotone object edge can cross at most 2 times m minus 1 horizontal or vertical divisions of m by m subpixels. And that means if you count the first one it was in, and then every other one has to be gotten by crossing one of those edges to see all the ones it goes through. So at most one more than that, 2m minus 1 plus 1, which is equal to 2m minus 2 plus 1, which is 2m minus 1. In any case, it's big O of m, which is big O of the square root of n. Right? If this is the number of subpixels, that's how many different squares the edge goes through. At most. Might be less. So what we're trying to estimate is the variance. Let me get my notes here. So our estimate IN is 1 over n times the sum k equals 1 to capital N, where k stands for one of these subpixel samples of f k, xk, yk. And the variance of IN then is going to be 1 over n squared times the variance of this sum. Now, each time you pick in these squares, you pick a subpixel sample. That subpixel sample for the next square is independent, right? The probability of getting a specific x and y here is independent of the probability of getting a specific x and y here. So, since the samples are independent, assuming you had a good random number generator, what I proved is if these are independent random variables, then the variance of the sum is the sum of the variance. But it needed the fact they were independent. Is the sum, well, 1 over n squared times the sum of the variance of f of xk, f of xk, yk. Right, okay, and we know that this variance is at most a quarter. Assuming that 1 is the brightest pixel you could get. And it was a black and white image. Obviously, you could do this for each color channel. But I can do better than that, because if I'm in one of these pixels where the edge doesn't intersect, this is completely black. So the variance I'm going to get here is 0. Right? I drew this curve over here for this Poisson case. If the probability is 0 of getting white, the variance is 0. And if it's a completely white pixel, the variance is 0 also, say in here. So the only terms which are non-zero are these at most 2m minus 1 terms, each of which is size maximum 1/4. And so what this is since this is O of the square root of n, factor here, we have the variance going as the, let's see, the square root of n over n squared, which is really big O of n to the minus 3/2. So the standard deviation, this is the sigma squared for n samples. If you want to know, the average sort of error you get, the standard deviation measures, how much you'd have an expected error for any given estimate like this compared to the true answer. That's equal to big O of n to the minus 3/4, the square root of that. But without jittering, it was big O of n to the minus 1/2. Right? Because if you put a random sample anywhere in here, separately, independently, for each of them without using jittering, then your area would be, your variance would be the same for all of them. It would be 1/4 for all of them. We'd have all of these terms instead of only, a small fraction, namely related to a one-dimensional line through this two-dimensional array. Okay, so I'm not going to have time to do the calculus to actually sample glossy reflection. Maybe I'll do that next time. But I do have time to say one thing. Namely, if this thing is constant, and this is cosine of the incoming direction and the normal at x, if you have something called environmental illumination, where you think of light coming from a sphere at infinity, and the object you're shading is very small compared to that sphere, so that the light coming in a given direction doesn't really depend on the position, because it's coming from objects that are far away, then this integral for diffuse reflection, say for environmental illumination at infinity. I don't know if you're familiar with like what they use for games where they have an environment sphere and they get perfect glossy, perfect mirror reflection by just looking up that direction in an environment map and seeing what's reflected from that reflected direction. So you create those environment maps. The book shows technologies for doing it on a section which we may or may not skip. Then this integral depends only on n at that position, because n is actually what's determining this hemisphere. And then this is a cosine weighted integral. This is a constant. I mean, you could get the environmental illumination, and then once you looked at that, so you save the actual hemisphere integration over the environment in another table that depends only on the normal direction, which is basically that cosine weighted integral over the hemisphere that you could pre-compute in a table. And then, instead of just only perfect reflections from the environment map, you could actually look up, according to the normal, the diffuse reflections from the environment map. So what I want to say is you can do the same for Phong reflections. Because if here's the plane, and here's the normal, and in Phong shading, he's using cosine to the n of the difference between the incoming direction and the perfect reflection. So here is the light going to your eye in direction theta. Here is a particular direction c, incoming. This was over the incoming directions. And what we're going to do is take the perfect mirror direction of that incoming direction r. So I didn't draw it very well, but let's see. This angle looks like it's flatter than that. Maybe this angle equals that angle. Here is r. Right? And this is the angle here, alpha, which we're taking the cosine of here. Well, it turns out if you take the perfect mirror reflection in the same normal of the viewing direction, and you get the perfect mirror of the viewing direction, then this angle is also equal, right? Because both of these rays reflect into both of these rays. So instead of thinking of cosine of this direction, we can think of cosine to the n of m and this incoming direction. Right? Now, in Fong's formula for it's really the BRDF is this cosine divided by this cosine, which is, you know, your foreshortening factor, because in Fong's shading formula he didn't have that foreshortening factor as part of the formula. So the BRDF times the cosine is what's equal to this number, which means this integral is just the L times cosine to the n of m psi. And this L is coming in from direction psi. And it's at the point x, but if it's environmental illumination, it doesn't depend on the point x because it's coming in from infinity. So that means, so now I've changed my formula on the board because I was running out of time, but the point is this depends only on m. Right? Because this is an integral over psi, and I've removed all the other dependencies. So that means you can actually pre-compute the glossy reflection, basically by blurring the environment map by the blur that corresponds to sort of like a convolution of this blur function times this angle here, where this is like the difference of angles here, which is my alpha. And so you can pre-compute that too in a sort of a glossy blur of the environment map. And then by just looking up in the environment map, you can get the diffuse reflection integral and the glossy reflection integral if you've pre-computed them. So this was a technique invented by Miller and Huffman about 18 years ago, and it's been used on some Hollywood films, to make glossy objects. Or, your environment map also gets you the perfect mirror reflection if you wanted that too. And so this is sort of like pre-computed radiance transfer, except it doesn't take advantage of occlusion of the environment by other objects nearby. Okay, that's it for today.